the amount of matter in an object. And that is different from volume. I have two cubes in my hands. I have this cube of solid gold, and I have this cube of balsa wood. And looking at them, how do you think their volume compares? Brandon?
They're the same.
Yeah, they're about the same. They're pretty close, the same size. Volume is the same. But one of these has much more matter in it than the other. Which one? Pass it on. Kimberly? Yeah. The block of gold. It has a lot more matter packed in to that same volume. And therefore, how does it feel when you pass them around? How do they compare? One's heavier than the other, yes. And when we say it's heavier, we're talking about mass. Now we have a law that applies. When we talk about matter, we have this law of conservation of matter. It also applies to energy. And it has three parts to it. The law of conservation of matter states, first off, matter cannot be created. I bet you can guess what the second part of the law says. Indeed? No. I mean, it is, but that's not the second part of the law. So matter cannot be created. Right? Matter cannot be destroyed. All right, so what can you do? Can only be transformed. So matter cannot be created or destroyed. It merely can be changed in form. Now you may say, it doesn't seem to make sense. If I take a piece of wood and I find its mass, I find out how much matter is there, and then I burn that piece of wood, aren't I destroying the matter that makes up that wood?
No.
No? What am I doing? Nicholas? I'm changing it into other forms. Some is changing to ash. What else is happening to that wood? The matter that makes up that wood, right?
Turning into smoke.
Into smoke and water. If I were able to find the mass of that piece of wood, then I'd burn it, but we're somehow able to capture all of the gases being released, the smoke, the water that's released, and so on. And I have the ashes left over. If I were to find the mass of the gas that I collected, along with the mass of the ashes, what do you think it would be equal to? Rosemary?
The mass was at the beginning.
Yeah, the original mass of that wood. I'm not actually destroying the matter. Just transforming it from one form into another. Okay, so it would be the same amount of matter. So that's what the law of conservation of matter says. It also applies to energy. We'll talk about that in a future unit. Energy cannot be created or destroyed, but merely transformed. All right, so as far as units in the metric system for mass, the base unit of the metric system of mass is grams. Okay. Generally, the prefixes we will use is milligram and kilogram. Okay? So milligram is 1/1000th of a gram. A kilogram is 1,000 grams. If you want a frame of reference, a kilogram is about 2.2 pounds. Okay, so about 2.2 pounds is a kilogram. A gram is about like a pen cap is about a gram or so. So that's how much a gram is. And milligram is very small. What do you often hear measured in milligrams? Anyone know anything that's often? I mean,
Smoke exploding.
okay. I mean, that would have a certain mass in milligrams, but you hear milligrams in sort of your everyday life in terms of what, Tom?
Like butter.
food is one place. Like if you look on the nutrition facts, the amount of salt in your food, the amount of sodium is measured in milligrams. Also medicines. You know, the doctor may give you a prescription to take, you know, or you may buy Advil at the store, and each pill is 200 milligrams of ibuprofen. So medicines are often dispensed in terms of milligrams. So to measure the mass of an object, we have two tools that we will be using. Okay. A balance. This is called a triple beam balance. Now, I thought you probably used these before. My last class said they hadn't. Have you ever used a triple beam balance?
No.
So in elementary school, you may have used like a pan balance.
Yes.
It works on the same principles, but it's a little bit different. So this is a balance, triple beam balance. We'll be using them tomorrow in class. And so just as far as the parts, the part where you place an object, right here, this is called the pan. Okay. These weights that you have that you can move back and forth, on ours there's 3. It's called triple beam balance because there's 3 beams with a weight on each. Those are called the riders. Now when there's nothing on the balance, there's nothing on the pan, the arm of the balance has a little pointer over here on the right side. It should align with the 0 mark. If it does not, there's a knob under here, the 0 knob, that you can turn. So turning the 0 knob will change where this pointer balances out. You want to always begin with the pointer at the 0 mark, when there's nothing on the balance and all the riders are at 0. Just zeroed out. Not quite. So you turn the knob a little bit, and it'll change how the marks align. Probably pretty good. All right. And then the pointer is at the end. Now you see something similar to this. I don't know. The doctors that I go to all have digital balances now. But does anyone at the doctor's office have the older? It's a triple beam balance basically. You stand on it. They slide the weights over until it balances out, and then it tells you your weight. Works on the same idea. All right. So to measure something using this triple beam balance, you take your op, you make sure first that it's at 0. If it doesn't, you adjust it using the 0 knob. Okay. Place your object on the pan, and it's going to go up. To find the mass of this banana, what do? Matt?
You slide the weights till it's at 0?
Yeah, I slide these weights until I can balance them. So I start with the biggest one, C. Okay, I can go up 1. And now with the largest rider and the medium one, there are notches. It has to be in a notch. All right, now I went to the second notch on the big one and it went all the way to the down. So what do I have to do? Yeah, I have to back that up 1. Okay. Then I go with the medium sized one. I start sliding it. Same thing. Okay. All right, that's going to be close. And then I use the smallest one, which slides freely. It doesn't have any notches. And I slide that until the pointer is pointing at 0 again. And you let it balance. It should be close. Yep. And then what? So I have it all balanced out. Now what do?
Then you like take the measurement of the riders?
Yeah, I add up all the riders. So this one is at 100. This one is at 60. This one is at 0.7. So what's the mass of this banana, Kimberly? 160.7 grams. This is measured in grams, right? So that's how triple beam balance works. We also have a digital balance that we sometimes use. Okay, and it's a little bit simpler to use. Okay, basically you plug it in if it doesn't have any batteries in it, which ours probably don't. Turn it on. Again, it has a pan to place your object, and then it will read you. Oh, first, so you turn it on. Then there's a button, the 0 button. You always want to make sure it reads 0 to begin. So then you press when there's nothing on there, you press the 0 button, place your object on there, and then it will give you the mass of that object in grams. So the parts are pretty simple. The pan, the 0 button, and then you have the display that reads you. Kimberly?
We can do that like in like stores to measure how much.
Yeah.
Like when we get meat, how much we.
Yep, they use a balance like that, a digital balance like that. Now, let's talk here for a minute. So if I have some liquid in this beaker, I want to know the mass of the liquid. What do? Pour it on the pan?
No.
Okay. How am I going to find the mass of the liquid only? Juliet? Exactly. I need to know the mass of a container, and then I put my liquid into it, find the mass of them together, and then what? Just subtract. Okay, so I would find the mass of this graduated cylinder. I pour my liquid in, find the mass again, subtract the two numbers to find the mass of just the liquid. Now, if I'm using a digital balance like this, I have an even simpler method I could use. Does anyone know what it is? Kimberly? Put the beaker on the pan. Well, before I do that, Habib? I don't even need to do that because of one of the buttons on this balance. Habib? Yeah, so if I put this beaker on here, it's going to give me a mass. Then I press the 0 button, it's going to reset back to 0 again. Now when I add my liquid, what the number that it gives me is going to be what?
Higher.
Well, it's going to be the mass of just the liquid because I zeroed it with the beaker on there. Okay, so that's an easier way to find the mass of a liquid. Put your container on there, press the 0 button, it'll go back to 0, then you place your liquid in there. Alright, so some simple examples. Let's say you have a triple beam balance in front of you, and these are the riders. They're in these positions. What mass is this top balance displaying? What's the mass if you were to read that triple beam balance? Caitlin?
70.
Not 70 grams. What's that? No. Look carefully. Peter?
175 grams.
175 grams. We add them all up. 100 plus 70 plus 5, 175 grams.
But does it being a little bit accurate before?
No, it's just because of the way it's drawn. On our balances, the one that goes up to 10, it just slides freely, and there are markings for each tenth of a gram, so you can get it more accurate.
So there's markings in between?
Yes, there's markings for every tenth of a gram on ours. Now the way I drew this, it doesn't have that. How about this bottom set? Chloe? 328 grams. Yep. Habib?
That's the thing. If you're off by 1, it'll still count.
1?
Yeah, like 1 gram.
Yes. No, it wouldn't count. You would get that wrong.
Okay.
Like, it's pretty clear what it is. All right, now, last thing for us to talk about today is mass versus weight. Because in our everyday language, we generally use those terms interchangeably. But they technically, scientifically, are not the same thing. Okay. So mass, as we said, what is the definition we're going to use for mass? Nat?
The amount of matter something else?
Yeah, the amount of matter in an object. How much stuff is there? That's what matter is. How much stuff is there? That's what mass is. How much matter there is that make up that object. And it doesn't change with your location. If I find my mass right now, and then I go to Neptune, is the amount of matter that make up my body, is that going to change?
No.
No. So it doesn't depend on location. It's generally measured in grams or kilograms. But weight is a little bit different. If I find my weight here right now, and then I go to Jupiter, is my weight going to change?
Yes.
Yeah.
Yes. So why? What is the difference then between mass and weight? Tom?
That weight is dependent on the gravitational force.
Yes. Weight is dependent on the force of gravity. And the force of gravity varies with your location in relation to a planet. Okay, so weight is determined by the mass of an object as well as the force of gravity pulling on that object. So they're certainly related. And that's why we sort of use them interchangeably in our everyday language. But in science, they're not technically the same, because weight takes gravity into account. So, the formula to determine the weight of an object is the mass of the object times the force of gravity at that location. Kimberly?
What if you had like an object and you put like for the basic example, like say you could have a tip on it and say it was empty and then you added water to it, would that change? Would that
Yeah, I mean then because you have a different object, but for a single object its mass doesn't change. Well, I would tell you, for example, on Earth, the force of gravity is 9.8 meters per second squared.
I'm still not the strongest force.
So, weight is a force, and it's often measured in terms of newtons, is the unit. Newtons, abbreviated capital N. For example, this spring scale here has grams on one side and newtons on the other. So if I find, so the mass of this object is about 210 grams, or 2.1 newtons is its weight. Okay? Now here we use them interchangeably because we're on Earth, but this weight is variable. Okay? And the force of gravity depends on two things: the mass of the object and the planet, if it's a planet that's exerting that force of gravity on it, and also the distance from the center of the planet. The farther away from the center of the planet you go, what happens to the force of gravity? It weakens. It decreases the farther from the center of the Earth. Yeah?
Wouldn't that help thing and then affect the weight?
No, because it's zero with the hook on it.
Okay.
Is that why when you fly, you have no gravity, it's
Yeah, because the farther you get away from the center of the earth, the force of gravity decreases and decreases until you're far enough away that there's no force of gravity. Or there's very little. All right, let's think about this then. If we have the earth and the moon, how does the gravity on earth, the force of gravity on earth compare to the force of gravity on the moon? Brandon?
The gravity on Earth is bigger.
Yeah, there's a greater force of gravity on earth, and therefore the weight of an object on earth versus the moon, Habib,
It's heavier
it's heavier where?
on Earth.
Yeah, the weight is greater on earth. Now, how about the mass of objects? How does that compare? Brian?
It's equal.
It's equal. If I take my banana to the moon, it's going to weigh less. But is there any less matter in it,
No.
whether it's here or on the moon? No, it's the same amount of matter. So its mass is the same regardless. But its weight is going to change. We think about another planet, Jupiter versus Earth. How does the gravity compare? Kimberly?
Jupiter is bigger.
Yes. The weight, the force of gravity on Jupiter is larger. Why is it larger on Jupiter? Brandon?
The planet is bigger.
Because it's a bigger planet, has a much greater mass. So weight on Jupiter would be greater. Mass of an object on Jupiter would
Equal.
be the same. Okay, how about if we think about on Earth? Would you have a different weight on the top of a mountain versus where you are right now?
No.
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 Would you weigh more or less if you're in a plane? Or if you're at the bottom of a very low valley? Would your weight change?
No.
So the force of gravity depends on two things. The mass of the planet. Does the mass of the Earth change?
No.
In your distance from the center of that planet? Yes. So if you're at the very top of a mountain, how would the force of gravity compare to in a deep valley? Caitlin? Be less. Force of gravity on a mountaintop is less than the force of gravity in a valley because you are what?
Higher altitude.
Farther away from the center of the Earth. So how would your weight vary? The top of a mountain, you measure your weight, you would weigh less. Now, would it be measurable? Maybe not. It would be a very small amount, but there would be a difference. Would your mass be any different though?
No.
No. That doesn't change. So, in summary, your mass doesn't change depending on location, but weight can. Now, I guess we shouldn't really say your mass never changes. Has your mass changed from 5 years ago?
Yeah.
Yeah, as you grow, your mass changes. But,
It's still four.
what's that?
Transform.
Oh, yeah, but you're increasing mass. That mass is being transformed from the food you eat into body tissue. All right, let's think about this as an example. The force of gravity on the moon is about 1/6 the force of gravity on the Earth, because the moon is a much smaller object. If you go to the moon, your mass is the same. You still have the same amount of matter in your body. But because the force of gravity is less, okay, your weight is about 1/6 of your weight on Earth. So we have a calculation here. On Earth, your mass was 70 kilograms. Okay? The force of gravity on Earth is 9.8 meters per second squared. So if we multiply force of gravity times mass, your weight on Earth might be about 787 newtons. Go ahead and fill in that for the moon. So what would it be for the moon, your mass and your weight? So if your mass was 70 kilograms on Earth, what would your mass be on the moon? Habib?
11.6666.
No? Caitlin? 70 kilograms. Right? Your mass does not change with your location, but your weight does. What would your weight be on the moon? Matt?
114.5 newtons.
Yeah, about 115 if we round newtons. About 1/6 of your weight on Earth. So again, your mass doesn't change with your location, but your weight does because of the force of gravity. I'm supposed to start playing video games.
Already played video games.
All right, now, force of gravity, like we said, on the moon is much less. But a person's muscles still exert the same amount of force that they did on Earth. So people can jump higher, okay, and need some time to adjust to a different force of gravity. Some of these videos show astronauts on the moon and how difficult it is to sort of move around with different force of gravity. This guy's trying to get up. So again, it takes certainly some adjustment.
He's flying.
Measure, hi, you got all the shields, you're coming out south. Verify each flow is level and line, it is aligned and all is good. UH to the LRD, LMP seats, and then what do I do? Let me see.
He doesn't need to carry that UHC back.
Fall.
Yeah, I'm gonna leave the UHP, get the heat flow in case you need it. Okay. Okay, I'm gonna go behind a rock over there. Down now. Hey, John, this is perfect with the limb and the roller and you and Stone Mountain and the old flag. Come on out here and give me a photo.
Taking a picture.
Take that easy look.
That's a
Off the ground, that's more. There we go. Good.
So the force of gravity pulling down after you jump is 1/6, so therefore you can stay airborne much longer. All right, one last slide here for this. So in this picture, obviously it's from many years ago, Mr. Arcuri just got done winning a bodybuilding contest, and the judges are weighing him to see if he competed in the proper weight class. So to determine Mr. Arcuri's weight, okay, he's at sea level on planet Earth where gravity is 9.81 meters per second squared. Okay, the scale reads 100 kilograms. So find his mass and his weight. So what is his mass? So 100 kilograms. What would his weight be? Really don't need a calculator for this one. Tom?
980 newtons.
981 newtons on Earth. So he continues to compete in an intergalactic bodybuilding competition. His first competition is at Mount Olympus on Mars, where the force of gravity is 3.75 meters per second squared. What is his mass and weight on Mars? What's his mass? Kayla?
100 kilograms.
Yep, and his weight?
375 newtons.
375 newtons. So it'll be less on Mars than it was on Earth. So on Earth, do bodybuilders and wrestlers actually compete in weight classes or mass classes? Sophia?
Math class.
Mass classes. Okay. I got one last video here. Oh, let's hold on. Well, we're gonna run out of time, but if you drop a feather and a hammer on Earth, which hits the ground first?
They're the same.
No. If I have a hammer and a feather and I drop them, which is going to hit the ground first?
Hammer.
The hammer. Is the same true on the moon? That's low. You got a feather in this hand? Hammer in that hand. Oh, we'll have to save the suspense for tomorrow.
Where did you get these videos?
What's that?
Where'd you get
Oh, I recorded them. I was there with them on the moon.
Oh my gosh, they hit the ground at the same time.
They did.